What would actually happen if we tried to build a star instead of just watching one form in the sky? Start with Jupiter, then bolt on a second one, then a third, and keep going until the darkness around you starts glowing on its own. For a long stretch of that process, nothing dramatic happens. You just get a bigger, colder ball of hydrogen and helium sitting quietly in space. Gravity is patient though, and once enough mass piles up, it stops making a bigger planet and starts making something that runs on its own internal fire. Building a star really comes down to one number: how much mass gravity needs before it can permanently trap fusion inside a core and keep squeezing that reaction into a steady burn. We already trigger fusion on Earth for a fraction of a second at a time, but a real star keeps that reaction running for billions of years with no lasers, magnets, or maintenance crew involved. Its structure comes from a permanent tug-of-war between gravity pulling everything inward and heat pushing everything outward, with neither side ever fully winning. We don't need to copy the sun down to the last detail, we just need to reproduce that exact balance, scaled up to an astronomical size. Nature starts this process inside molecular clouds, vast reservoirs of hydrogen, helium, dust, and complex molecules drifting through space at brutally low temperatures. These clouds look almost empty by earthly standards, yet they hold enough matter to spin out hundreds or thousands of stars once gravity concentrates a dense enough patch. Once a region starts collapsing, every particle falls toward the shared center of mass, turning gravitational energy into motion and then into heat through endless collisions. The cloud never shrinks into a neat sphere, because even a slight starting spin accelerates as the material contracts, the same way a skater speeds up by pulling in their arms. Most of the falling matter flattens into a spinning disk, while magnetic fields and violent jets carry off the angular momentum that would otherwise stall the whole collapse. Deep inside this spinning construction site, the central object keeps growing denser and hotter until it becomes a protostar, buried under the leftovers of its own formation. A protostar already glows, but that early light comes from gravitational contraction alone, long before any fusion reaction switches on inside it. Gravity keeps squeezing the core, driving its temperature up until hydrogen nuclei move fast enough to challenge their own electrical repulsion. They never actually need to cross that barrier the classical way, because quantum tunneling lets a small fraction of them fuse without a direct hit. Once those reactions release enough energy to stop the contraction, the object settles into equilibrium and begins the long, stable stretch we call a stellar life. All of this sounds simple to recreate: gather hydrogen, compress it, let gravity finish the job, wait for the center to catch. The hard part hides in that first word: gather. The smallest true stars still need somewhere around 75 to 80 times the mass of Jupiter packed into their core. That's about 25,000 Earths worth of matter, squeezed into an object only a bit larger than Jupiter itself, because gravity adds density, not width. Fall short of that threshold, and the core never gets hot enough for sustained fusion, no matter how enormous the object looks next to an ordinary planet. Instead, it becomes a brown dwarf, a heavyweight bigger than any planet, but denied the central engine that turns an object into a star. Some brown dwarfs briefly fuse deuterium, a heavier form of hydrogen, but that fuel runs out fast and never kicks off the long-lived hydrogen cycle a real star needs. As more mass piles into a brown dwarf, its interior gets so compressed that the electrons inside start resisting being crammed into the same quantum states. That resistance, electron degeneracy pressure, holds the object up before hydrogen ignition ever gets the chance, drawing a hard line between the failed stars and the real ones. A star's core also has to hold up its own fusion without outside help. Take away whatever machine was squeezing it from outside, and only a genuine star keeps burning on its own weight. That's the actual definition of a star: self-gravity supplying the confinement, temperature, and pressure needed to keep its own reactions running. Which instantly rules out a tabletop star, because shrinking the mass takes away the exact gravitational force that makes the whole balance work in the first place. A miniature sphere heated to the sun's core temperature would blast outward, expand violently, and cool long before fusion could ever catch up and replace the lost heat. Holding it together would take outside pressure, and whatever supplied that pressure would become the real machine, with the glowing plasma inside acting as nothing more than its cargo. The smallest possible artificial star wouldn't fit under a mountain or inside Earth. It would come in at roughly Jupiter's diameter. The raw material is the bigger headache, because the solar system doesn't hold anywhere near enough loose hydrogen to build one without tearing apart existing worlds first. Jupiter alone supplies only a little over 1% of the mass needed, so swallowing it whole would just mark the beginning of construction, not the finish. Add Saturn, Uranus, Neptune, every moon, every asteroid, and the entire planetary lineup together, and the total still falls drastically short of the ignition threshold. The Sun itself holds more than 99% of all the mass in the solar system, which is exactly where almost every local star-building plan runs straight into a wall. We already have a star's worth of material sitting nearby. It's just already locked away inside the very star we'd be trying to copy. Reaching into interstellar space for fresh fuel fares no better, since the distances between useful concentrations of matter dwarf the size of anything humans could ever build. Even dense interstellar clouds spread their mass across light years, which means collecting them takes machines working across volumes bigger than entire planetary systems. Every atom gathered this way would then need its direction redirected toward the build site without heating up, scattering, or drifting off along the journey. Moving 75 Jupiters worth of matter also means handling an enormous amount of gravitational energy, since every new layer accelerates faster and slams into the object harder as it grows. That impact energy isn't wasted, it's exactly what heats the interior. But released carelessly, it turns the entire build site into a storm of radiation and expelled plasma. The forming star ends up looking a lot like a natural protostar anyway, wrapped in an accretion disk, magnetic turbulence, jets, and gas crashing in from every direction. Engineers wouldn't bolt this together piece by piece like a bridge. They'd steer a controlled collapse and keep the falling matter from simply escaping again. Angular momentum becomes the biggest enemy in the whole project because matter arriving from different directions almost never falls straight toward the center. Gas carrying too much sideways motion just settles into orbit instead of falling in, building an ever-expanding disk around the unfinished star. Nature solves this with friction, magnetic fields, gravitational interactions, and jets that throw off part of the material specifically to shed its angular momentum. An artificial system has to force the same trade-off, sacrificing some of the collected mass so the rest keeps moving inward. Temperature control creates the opposite problem, because the interior needs to heat up while the surrounding structure needs to shed enough energy to stay gravitationally bound. Too much heat and the pressure swells the protostar and stalls its contraction. Too much cooling and gravity crushes the material into an even denser configuration. None of this needs a giant match, a nuclear trigger, or an ignition laser, because past a certain mass, the object lights itself as an unavoidable result of being compressed. Dropping matter onto it keeps supplying gravitational energy until the central temperature hits millions of degrees and hydrogen fusion switches on naturally. What the newborn star ends up looking like depends on its composition, since hydrogen is the long-lived fuel while helium and heavier elements reshape its opacity, structure, and how it moves energy. Dumping rocky planets into the mixture doesn't stop the star from forming. Their minerals just vaporize, split into nuclei and electrons, and join the interior plasma. Those heavier elements only ever add a tiny sliver of the needed mass, leaving hydrogen and helium as the only materials doing the real bulk work. Near the ignition threshold, the finished star shines far fainter and cooler than the Sun, radiating most of its energy out as deep red and infrared light. Its surface still sits at thousands of degrees, while its center stays pressurized enough to keep fusing hydrogen at a slow, tightly controlled pace. That slow pace is exactly what keeps a star alive, because its fuel reserves are vast, but the reactions burning through them are individually reluctant to the point of absurdity. The proton-proton chain kicks off when two protons interact through the weak nuclear force, an event so rare that a single proton waits an immense stretch of time before its turn ever comes. A star gets around that reluctance through sheer numbers, packing so many particles into its core that rare reactions still add up to a non-stop flood of energy. That's exactly why the Sun keeps shining steadily for billions of years instead of tearing through its hydrogen in one catastrophic flash. A minimum mass red dwarf burns even more patiently, stirring material through nearly its entire interior and reaching a far bigger share of its total hydrogen supply. A star like that survives for trillions of years, outlasting the Sun by an enormous margin and burning on long after today's galaxies have transformed beyond recognition. From an engineering angle, that kind of durability looks incredible. Build the smallest working star and get an unbelievably stable power source with zero moving parts. From literally every other angle, it's a ridiculous power plant, since its fuel mass dwarfs anything civilization actually needs while its energy sprays outward in every direction at once. Parking it anywhere near Earth would wreck the neighborhood long before ignition even finished. its gravity yanking every planetary orbit into a brand new arrangement. Even at a carefully chosen distance, the new star would force Earth and every other planet to orbit a shifted, shared center of mass. Just building it would flood the surrounding region with heat, radiation, charged particles, and debris shed from the growing accretion disk. Building it safely means picking an isolated region far from any inhabited system, which also means parking its energy just as far from whoever's supposed to use it. Shipping that energy across interstellar distances loses so much and demands so much infrastructure that ordinary stars stay the more practical option by a wide margin. The universe is already crammed with stars, and nature hands them out for free without asking anyone to gather 25,000 Earths worth of fuel first. A civilization chasing stellar energy gains more by wrapping collectors around a star that already exists than by building a brand new one out of scattered gas. Massive fleets of orbiting habitats and power stations can intercept a growing share of a star's light without ever needing a rigid shell wrapped around it. That kind of system still counts as engineering on a jaw-dropping scale, except it runs off a fusion source that's already switched on instead of one built from raw material. Artificial sun describes something much smaller and far more realistic than an artificial star. A reactor that copies the reaction while swapping out gravity for technology. On Earth, fusion machines heat light atomic nuclei until their electrons strip away entirely, producing a plasma no ordinary wall could touch without instantly cooling it down. Magnetic confinement reactors steer that plasma with powerful fields, spiraling charged particles inside a chamber shaped to keep them clear of the walls. Inertial confinement takes the opposite route, crushing a tiny fuel capsule so fast that fusion ignites before the material even has time to fly apart. Both methods borrow a slice of stellar physics, but neither one produces a self-gravitating object or reproduces the balance that gives a star its shape. The real challenge comes down to three connected demands. Get the fuel hot enough, keep it dense enough, and hold it together long enough for fusion to pay back the energy invested. Stars satisfy all three through raw mass alone, while reactors chase the same result with magnets, lasers, precision hardware, and constant active control. That's exactly why stellar fusion looks effortless from a distance, while terrestrial fusion remains one of the hardest engineering problems humans have ever attempted. The sun's core alone is bigger than Earth, buried under hundreds of thousands of kilometers of plasma pressing down on it from every side. Human reactors work with a sliver of that fuel, so every instability, impurity, and stray collision has an immediate, visible effect on performance. A true artificial star solves confinement by drowning the whole problem in gravity, but getting that much gravity together costs far more than the solution is worth. Building a reactor tackles the hard physics head-on, while building a star just trades precision for an almost incomprehensible pile of matter. There's one shortcut that sounds tempting: grab an existing gas giant and keep adding mass to it until hydrogen ignition kicks in. This skips assembling a core from scratch, but the planet still needs dozens of extra Jupiter masses delivered from somewhere outside its own system. As that added gas piles on, the former planet heats up, contracts, and loses the layered structure that used to make it recognizably a planet. By the time fusion stabilizes, nothing planetary remains at all. The project has quietly turned a gas giant into a red dwarf through controlled accretion. Another route starts with a natural brown dwarf already sitting just under the ignition line, cutting down how much extra material the whole project actually needs. Feeding that object a few more Jupiter masses pushes its core across the threshold and flips a failed star into a fully working one. That's the closest the universe gets to lighting a dormant furnace, though reaching, moving, and feeding an object like that still takes an industry running on an interstellar scale. The switch on wouldn't look like some cinematic flash. Rising pressure gradually cranks up fusion until the interior settles into a stable balance on its own. Surface brightness climbs as that energy works its way outward through dense plasma, finally escaping after a journey far longer than the reactions that produced it in the first place. Once it's running, the star needs no control room, but calling it maintenance-free ignores that its output, orbit, magnetic activity, and surroundings still all demand active management. Stars throw off flares, stellar wind, ultraviolet light, and streams of charged particles that interact directly with whatever planets or structures sit nearby. A small red dwarf also keeps its habitable zone uncomfortably close to its surface, where tidal forces and stellar activity make life difficult for anything orbiting there. Finishing the star, in other words, is really just stage one of building an entire safe system around it. Builders still need stable orbits, radiation shielding, heat management, fuel collection networks, and some way to stop leftover material from slamming into inhabited structures. By the time a civilization has all of that in hand, it already commands planets, asteroids, interstellar transport, and energy systems that go far beyond anything one new star provides. The whole project starts to resemble building an ocean after already mastering water, driven less by necessity than by the urge to reshape nature at its deepest possible scale. Even so, an artificial star earns its keep as a thought experiment because it strips away the familiar light and shows exactly what a star is underneath. What separates a star from a bigger campfire is the kind of reaction running inside it. Flames just rearrange electrons in ordinary chemistry, while a star's core rebuilds atomic nuclei themselves and caches in the energy locked inside their binding. Hot plasma alone isn't the answer either, since plenty of plasma exists across the universe without ever becoming a star, dispersing the instant whatever confines it lets go. A star is really a gravitational system where compression creates heat, heat drives fusion, and fusion pushes back just hard enough to keep gravity from finishing the collapse. Strip away too much mass and the nuclear engine never stabilizes. Pile on far more and the star burns faster, runs hotter, and cuts its own life dramatically short. Mass acts as both the building material and the control system, setting a star's pressure, temperature, brightness, color, and eventual lifespan all in one shot. Engineers only get to choose those properties once, by picking mass and composition before the object settles into its final equilibrium. After that point, changing a star means adding matter, removing matter, altering its spin, or interfering with flows that carry the energy of entire worlds. Removing mass opens up one of the boldest forms of stellar engineering, called starlifting, where magnetic fields and controlled heating pull plasma straight off a star's surface. That harvested material supplies fuel and raw elements while gradually reshaping the star's mass, brightness, and remaining lifespan. A civilization running starlifting gains a second route to an artificial star by shifting matter out of an existing star into a separate gravitational reservoir. Instead of hunting for loose hydrogen across interstellar space, it splits one natural star into several smaller, longer-lived ones. Turning a sun-like star into a handful of red dwarfs spreads its fuel among stars that burn hydrogen far more efficiently and last vastly longer. The whole operation stays extreme, but it reveals something surprising. Redesigning a star that already exists beats starting from empty space every single time. Nature already concentrated the material, ran the collapse, shed the excess spin, and kept the result burning for billions of years before any engineer ever showed up. Our role shifts from creator to sculptor, reshaping the mass and surroundings of a machine gravity already assembled on its own. Even the word build gets slippery here, since guiding forces that already exist is exactly how almost every large human structure gets made in the first place. We don't invent the strength inside steel or the gravity holding up a dam. We arrange matter so the laws already running the universe produce the outcome we want. Star construction runs on that exact same principle, just scaled up until the tools are entire planetary systems and the building material arrives by the mass of whole worlds. The blueprint fits into a single sentence. Gather enough hydrogen, control its spin and heat loss, then let gravity compress it into fusion that sustains itself. Every word in that sentence hides an industry bigger than human civilization, stretching from interstellar mining to managing energy that can sterilize entire planets. Physics puts no mysterious lock on this process since stars form constantly out of ordinary matter, following laws we already understand completely. The real barrier is scale, and scale turns this from advanced engineering into coordinating the movement of a serious fraction of an entire solar system. Long before humanity commands that kind of power, we'll build machines that fuse atoms without becoming stars, and harvest starlight without ever owning the star producing it. Those achievements hand us nearly every practical benefit an artificial star could offer, without the burden of manufacturing gravity strong enough to build one from scratch. If some distant civilization ever finishes the whole project, the result won't carry visible seams, supports, or machinery announcing where it came from. It'll just look like a small red star, quietly burning for trillions of years, indistinguishable from every other one gravity assembled inside an ancient cloud. Only its position, its exact composition, or some carefully engineered surroundings will ever give away that this point of light began not with a collapsing nebula, but with a decision.